Let's get started with quantum computation and no cloning today. Alright, so last time we already talked a little bit about the basics of quantum information. We defined a qubit, right, and we discussed how to represent multiple qubits. We discussed a little bit about the origins of quantum mechanics and so on and so forth. And the plan from today onwards is to go deeper into this formalism so that we can understand mathematically what all these fancy sounding properties of quantum computation, what do they really mean, right, how do they really manifest. So that is our plan for today. So one basic question that we need to answer, right, as soon as you define as soon as you define the notion of data, whether it be bit, whether it be qubit, you would like to compute on it, obviously, right. That's really the whole point, that the whole point of studying this. So the first thing that we'll try to understand today is what operations can we do on quantum states. So what do you think? I mean, what is a basic minimum that you should be able to do? Any thoughts? All the classical computation, right, and that makes perfect sense. So obviously we want the promise that we are studying this with is that quantum computers appear to be much more powerful than classical computers. So at the very least you would like to be able to do whatever basic things you could do on classical computers. There is also a few extra things that you should be able to do with a quantum computer just because of the way that we have set it up. So one simple thing that we need to we can do is a phase shift. Okay, so this is a very simple single qubit operation, and the physical motivation for it comes from the fact that if you change the material in the double slit experiment, then the diffraction pattern could change. So we will not go into the physics of this, we will just stick with the math, right. So the idea is simply that I want to be able to somehow mathematically capture a change in the diffraction pattern, okay. And what this is represented by is by multiplying, as you see in written here, by multiplying one of the two amplitudes by a phase shift, okay. So what is our phase shift? It's e to the I theta. So theta here is the angle by which the pattern will get shifted, and when you multiply this e to the I theta, it is basically going to be on one of the two amplitudes, okay. So what this will do is it will take 0 plus 1 over root 2 to 0 plus e to the I theta 1 over root 2, okay. So now this is just saying what happens when this phase shift occurs, right. So if I started with this, then after the phase shift I get this. So this is fine, but how do I mathematically represent this? So we can write this phase shift operation using a matrix, okay. So let us try to write this. So I claim that this matrix will capture this operation, and it is easy enough to see. So I have let us say this is my phase shift operator, right, and this is the state, the quantum state. Then what does this give me? So just a simple matrix multiplication. So it is going to give me alpha e to the I theta beta, right, and this is exactly what we had over here. Yeah, so this is the phase shift operation, and here really any theta is fine. So let us look at a couple of examples here. Okay, so let us say that theta is equal to pi. In that case, e to the I theta is equal to minus 1. Okay, this is simple, just expand the e to the I theta and you can see it. So what does this do? So now if I have alpha 0 plus beta 1, then this is going to go to alpha 0 minus beta 1, just by definition. Does everyone agree with that? Right. So this is just simple. So similarly, if I have theta equal to pi over 2, In that case, e to the I theta is simply equal to I, okay. And this is going to take alpha 0 plus beta 1 to alpha 0 plus I beta 1. So, you are going to see that this phase shift operation is actually going to turn out to be important. One aspect of it that we can already make a note about is that this is something which is different from classical, right. So, it is something which is already new in some sense, and we are going to see that it is going to be important for us going forward. Now, another thing that we can certainly do is a bit flip operation. Okay, so now bit flipping is very easy. I mean, even classically we do bit flips via the NOT gate, right. So, what is a bit flip supposed to do? It will just take 0 to 1 and 1 to 0, right. This is the classical NOT gate. So, here in the quantum setting, we also have we also have a way to do it, and this is going to be via this matrix. So, as we can see here, I mean, if I have 0 1 1 0 alpha beta, then this takes me to beta alpha, right. Okay, and this is this matrix is called the poly X matrix. So, you can see here that there is a sort of natural analog of the classical NOT gate. So, classical NOT just takes 0 to 1 1 to 0. This does the same thing, but in the quantum setting. Okay. So, what have we done which is sort of different from the classical setting in the case of NOT? We are using this matrix as the operator. Okay. And as we will see today, representing these different operations using matrices is something that is going to be important in the quantum setting. We will talk about that. Are there any questions so far? So, we just saw two simple, very simple things. One was a phase shift, which was a little bit different than what we had seen before. One was a bit flip, which is exactly the same as something we have seen before. Okay, now again let us look at something which is important and which is different. So, remember last time we talked about the standard basis and the Hadamard basis, right. So, one thing that you certainly expect to be able to do is go back and forth between these bases, right. So, the Hadamard transform is another operation which allows you to go from the standard basis to the Hadamard basis. Okay, so this is how we represent it. So, as we can see here, so basically this is our starting state. Okay, this is the Hadamard transform, right, and this is our final state. So, we can again, we want to represent this Hadamard transform using a matrix. So, any guesses on what this matrix should be? So, I want this matrix, how did we do it before? We have a matrix times a state and this gives us the new state, right. So, now we want to change the standard basis to the Hadamard basis, and this Hadamard transform is really amazing. Okay, so we are going to see it sort of all over the place. It turns out that it will play a very crucial role in what we call the quantum Fourier transform, and this quantum Fourier transform is going to lie at the heart of many of the quantum algorithms that we see, okay, including Shor's algorithm. So, for now we are just defining this Hadamard transform. So, once again we want to write it down as a matrix. So, let us do that. So, I think I already have it, good. So, here is the matrix representation of the Hadamard transform. Okay, so you can check. So, here is my matrix, right. So, now if I take 0, right. So, 1 0. Remember, so ket 0 is represented by vector 1 0. So, what does this give me? So, 1 over root 2 1 1, right, and this is 1 over root 2 0 plus 1, isn't it? And this is the plus state. Yeah. So, this is our Hadamard matrix. And one cool property of the Hadamard matrix is that, you know, if you apply it twice, then you recover back what you already had. So, that is what we have over here. Okay. So, you can again you know check this out. So, if I consider the product of these two matrices, you know, I am going to get this. I am just going to get the identity matrix. Is that fine? So, this is the Hadamard transform. And now obviously, you know, I want to be able to do more general transformations. So, now we will try to understand that for a given qubit. So, I am still not talking of multiple qubits, I am still just talking of a single qubit, but in the case of a single qubit, what can my arbitrary transform look like? So, for those of you who have not seen this before, do you have any thoughts on what this transform should satisfy? I mean, there must be some properties. See, the intuition for this is again physical, right? Basically, I have a qubit which is a physical object. It has a certain, you know, it's defined in a certain way, and we had a certain normalization constraint, right? So, we had alpha 0 plus beta 1, we had alpha squared plus beta squared equal to 1. And why was that? It was because we need the probabilities to add up, right? So, if I observe something with one state with probability alpha squared, then I should observe the other one with 1 minus alpha squared, otherwise the whole thing does not add up, right. So, this was our condition for a qubit. This was, so now one basic thing that we might ask for just as a sanity check, isn't it, is that if I perform any operation on a qubit, this normalization should not die, right. It cannot be a valid qubit if the normalization goes away. And it will turn out that yeah, so basically that is the constraint that we need to satisfy, and you can, by the way, go back and check that the transforms that we have seen so far, they do satisfy that. Okay. So, that is a basic sanity check that we can do. Now, let us try to formalize this constraint in a more arbitrary way, right. So, now here I have these two you know, I have this transformation. So, 0 goes to u000 plus u011 and 1 as written here. So, now what I want to do is I want to come up with some condition on these u's, that is my goal, right. So, that I can say that when these conditions are satisfied, at that time this you know, this operation is a legitimate, a valid operation. Okay, that's going to be our goal. So, let us you know, work this out. So, let me put these u's together into a matrix. So, we have, you know, u00, u01, u10, u11. Okay, and now I want that for any state psi, right, it should be the case that u psi is a valid qubit. This is what I want, right. So, now once again let me you know set up some notation for psi. So, let us say you know alpha 0 plus beta 1, yeah, and now when I apply this matrix to this state, then what do I get? I get you know u00 alpha, right, plus u10 beta and u01 alpha plus u11 beta, right, and let me call this new state as phi. Okay, so this is my new state. And now I am going to impose the constraint that this resulting state is valid, and then we will work backwards to see what that gives us on U. So, in order for it to be valid, what do I need to say? So, you know, I can say that for being valid, it should be the case that this let me write it a little differently here, yeah. So, phi dagger phi should be equal to 1, right. This is the normalization constraint that we are after, right. So, now what does this give me? So, now I can write this in terms of my u psi, right. So, this dagger, this should give me 1, okay, and this in turn means I mean just expanding it out. This gives me the condition that psi dagger u psi is equal to 1, yeah. So, now the question is you know, what all u's are permitted. Now, I could call this matrix u dagger u m, okay, and I want it to be the case that you know, if I write, so let me write this as, you know, some m over here. Let me set up a little bit of notation, m00, m01, m10, m11. I want this to be equal to 1, right. Okay, any ideas on how to proceed? Now, so far what have we done? I mean, we just did a little bit of algebra, you know, opening out things, sort of first writing them using this matrix vector notation and then opening it out. Now, what am I finally after? I am finally after some condition on the u's, right. So, any thoughts on how I could proceed from here? He said is that we already know that, you know, mod alpha squared plus mod beta squared is equal to 1, right. So, we know this. We know this, right. And what he is saying is that by using this property, I can actually conclude that this matrix is the identity. Do you all see why we can conclude this? So, in particular, this condition has to hold for all values of alpha and beta, right, as long as it is a valid qubit. I mean, as long as this normalization condition holds, right, it is a valid qubit, and then for any such valid qubit I need to recover this equation. So, by trying out, for example, different values of alpha and beta, I could come up with constraints on m. So, what he is saying is that basically you know, if I fix, let me try to rephrase what he was saying here, let us see if this can work. So, what he was saying, I think, is that, you know, if I fix this alpha star beta star, right, then whatever you know, whatever this stuff is should end up as alpha beta the column, because that and that alone will give me a 1, right, and that implies that this matrix should be an identity. Okay. So, indeed it is the case that this matrix is, you know, we require it to be an identity for this condition to hold for all alphas and all valid alphas and betas, and this in particular implies that, you know, this matrix M, what was it? It was u dagger u, right. By the way, you can also flip you know, flip it around. So, you can also impose the same constraint on u dagger, you can check this yourselves, and this means that the condition I have ended up with is that u dagger u is equal to u dagger is equal to I. This is the condition that I ended up with, and this is exactly the definition of a unitary matrix. Okay, so a unitary matrix is a matrix which satisfies exactly the condition that we derived. All right. Yeah, so this if and only if is pretty simple, right. So this will only happen if u dagger is equal to u inverse. And unitary matrices are going to play a very important role for us. So it will turn out, I think I even have it here, it will turn out that any unitary matrix corresponds a valid operation on a qubit. So we already saw that a valid operation can be represented using this unitary matrix, and any unitary matrix is also a valid operation. So this is very cool already, right. So why is it cool? I mean, we already have a handle on how to work with qubits. How can I compute with qubits? Maybe it's not still sounding sort of super powerful, but at least it's a beginning. So given a qubit, I can always sort of change it to another qubit by applying some kind of unitary transform, and the unitary transform has the definition that we just discussed. Now another important matrix that we'll see in the course is a Hermitian matrix. I am just going to define it for now and leave it at that. So this is when u is equal to u dagger. Okay. All right, good. Now there was a small exercise which I wanted us to do, which is that show that if u is a unitary matrix, then it preserves norm. So we already sort of did this in the previous slide. You could, maybe it's just worth writing down once more. Okay, so I am just going to look at the norm of this resultant state, right, and that opens up using this inner product. Now this inner product I claim I can rewrite in this way. Does everyone see why? So this is just by linear algebra, right, and I will let you check it on your own. And now this is I, right, so this is the same as this. Okay.